All right, good morning, everybody. If you have problems hearing me, just let me know. I have a different microphone today. So if it's problematic, just let me know. I can switch back to the one that I've been using all semester. All right, so today's class, because the chapter is so short and because I'm not expecting a lot from this chapter, will actually not be terribly long unless you have questions that you want to ask at the end of it. And so today's is the last day for new content. So you can take a second to celebrate there. There's nothing else new that we're doing this week. Tuesday and Wednesday, we're just going to do the review. And you can find that review on the Moodle page. I think it's on the quizzes and exams page, and it's called the Final Exam Review Bazinga. So we'll work through those problems tomorrow and on Wednesday. And on Thursday, there will be no lecture. That will be either time for you to study or take the exam. So in a traditional summer class, the last day of the class is the exam day. So you actually will have not class that day. That's what we usually do. Week 5 homework is due today if you already or have not already turned it in. And then if you, well, most of you, everybody, I think, turn in the retro synthesis. So you can check Moodle for feedback. So I commented on your synthesis if there's steps that might not work or things that you can switch things around to make it work. There should be feedback on there for you. And then you want to use that feedback on your total synthesis molecule poster, which will be due August 1st. And that is worth 80 points of your lab grade. And then again, there's Thursday no lecture, and your final exam, which is cumulative, will open on Thursday as well. Does anybody have questions on any of the announcements? All right. Here is the answers to the quiz that we just had last weekend. So you can check those over if there's any questions there. For the first, or 2A, I think just about everybody got the nomenclature one, but for 2A, if you react an amine with methyl iodide, that is just going to keep reacting. Some of you had it doing an elimination, and that would be true if you used silver oxide after that. But right now, as it is, it's just going to form the quaternary ammonium salt. All right, and does anybody have questions on any of the other quiz questions? I think for most people did pretty well on the rest of it. Maybe a couple hiccups in the synthesis, but overall it was okay. All right, so let's look at our chapter 25 recap here. So alpha amino acids are very important to us in our biological processes. There's 20 naturally occurring ones, and they are building blocks of proteins. So a protein is a polymer of amino acids, and amino acids can also act as an acid or a base. And when it's acting as a base, a random OH, either from another amino acid or one in solution, can grab a proton off of the ammonium ion. And then it will form this, this O minus here, plus water. And then here it's acting as an acid. Oops, I'm sorry. This is acting as an acid. This is base. I was looking at the OH minus there. So here it's acting as a base where the O- is grabbing the hydrogen ion, and then it forms the ammonium down here. The functional groups are separated only by one carbon atom, and we've seen alpha carbons in chapter 22, that carbon next to the carbonyl. This is the same thing, which is why it's an alpha amino acid. So the groups are coming off of the alpha carbon. We have an amine group and the carboxylic acid and a side chain, which makes it an alpha amino acids. In nature and in synthetic compounds, there's all kinds of alpha or amino acids in general, and that can be any compound that has an amine group, the NH2, and a carboxylic acid. So anything that has those two things can be an amino acid, but to have this alpha amino acid, we're going to see the 4 things attached to this one alpha carbon. There's different acidities associated with each amino acid. So we start with this middle one here. This is what you would see at pH 7.3 or physiological pH. And at that pH, an ammonium is protonated. So we have NH3, and the carboxylic acid is going to be deprotonated. So that's what happens at the pH of 7.3. At the higher pH, so there's less protons available, this N becomes deprotonated. So this might be at pH of 11. So the O- is still deprotonated and the N is deprotonated. And if there's lots of protons around where it's acidic, which is pH 1 or 2, both of those things will be protonated. So your carboxylic acid is protonated, as is the NH2. All right, questions there? So these are all of the naturally occurring amino acids, and they're categorized into 4 different subgroups. One is polar, which means that all these side chains have polar groups on them. We have, those are all the alpha amines, sorry. This OH here for serine, threonine has a secondary hydroxyl group. This is a thiol group, so that's cysteine. Asparagine has an amide. Glutamine has an amide. And then tyrosine has the phenol group on there. So those are all of your polar amino acids. And maybe you'll want to revisit this page or this infographic on in the fall when you're taking biochemistry and you have to memorize the amino acids. It might come in handy there. Maybe not, I don't know. And then we have non-polar side chains. And those are side chains. For glycine, that's the only one that is not chiral, because the side chain is just the H. For alanine, we have a CH3. Valine is the isopropyl group. Leucine has an isobutyl group, which is backwards for naming versus isoleucine, which has the sec-butyl. Methionine has a CH2S methionine, or S-methyl. And then phenylalanine has a CH2 phenyl group, and then tryptophan is the tricky one that has an indole group on it. And then proline is one where the side chain connects to the amine, which is the only amino acid that does that. We also have electrically charged side chains. And these are usually our acid base ones. The 2 orange ones are your acidic protons. So that has a carboxylate, this has a carboxylate. The difference between aspartic acid and glutamic acid is the number of carbons in between there. Lysine, so these are your acidic. And then you have basic ones. Lysine has the NH3 at the end. And notice these are, that one's gonna be protonated the way that the NH is. So we'll see a couple examples of those when we're drawing the different Zwitter ions. And then we have arginine has a group with a guanidine at the end. There's that carbon double bond N with 2 other N's there. And then there's histidine. So these amino acids can act as bases in biological systems to get reactions to go. All right, and then there's different levels of protein structure. We have primary, which is just the amino acid sequence, and the order of those is very important. So if you change the order up, that's going to change the properties of the amino acid or the protein. A secondary protein structure is the alpha helix and the beta helix, and those are held together by secondary bonds, hydrogen bonds in the backbone. So you can see these are the primary over here. And then we have secondary structure. So those are hydrogen bonds that form between the carbonyl and the NH. And then we have tertiary, which is the secondary structure that folds on itself. And those can have hydrogen bond interactions, salt bridges, hydrophobic interactions, disulfide links. So this would be between different cysteines. And then we can also have metal ion coordination. So 2 carboxylates can be bound together by something like magnesium 2+. And quaternary structure is something like hemoglobin, where several tertiary structures come together. And this is the example of the different tertiary structure interactions. So you can see the disulfide bond that occurs between 2 cysteines. Electrostatic interactions or salt bridges happen between an aspartic acid side chain, the carboxylate, and then an NH3 plus of lysine. Hydrogen bonding can occur between an amide carbonyl and an alcohol hydrogen. And then hydrophobic interactions will occur between the nonpolar side chains. And then here's that example of the metal ion coordination. All right, and then something that you'll see also in biochemistry that we won't spend a lot of time on here is the catalytic triad. And that is amino acids that can do reactions in your biological systems to help enzymes and things like that along the way. So these different amino acids, these 3, serine, histidine, and aspartic acid, are ones that will sit in some enzyme pocket, in an active site pocket, and they facilitate reactions. So the serine is acting as the nucleophile, histidine is acting as a base, and aspartic acid acts as an acid. So what we are seeing here is, this is, what is this? Over here, I think this is aspartic acid. We have serine right here acting as a base, or the nucleophile, and we have things that are forming tetrahedral intermediates. So you can kind of follow the arrows here, and these are reactions and mechanisms that we've seen already in this class. Here, this NH2 is acting as a leaving group. So when you're in biochemistry trying to figure out cycles that you're having to memorize, it will help if you have seen these mechanisms, and you can put the mechanisms that you learned here into use in biochemistry, so you're not having to memorize so much. So for this class, you don't really need to know much about this. This is just kind of giving you an introduction a little bit into what you'll be seeing. Questions there? All right, so the first one, we draw a bond line structure showing the Zwitter ionic form of the following amino acid. So the Zwitter ion means that there are, 2 charges, could be more, and This one doesn't show at what pH, so we'll say physiological pH. So that is 7.4 or 7.3, 7.34, I think maybe is what it is. So if you recall, at pH 7.34, the pKa of this carboxylic acid is around 5. pKa of an amine is around 38. So at the pH, this one's probably around that as well. So at pH 7, anything that is below, so this pKa here of 5 is going to be deprotonated. The N is way over 7, so that one's going to be protonated. That will become NH3+. And then we can put 2 H's here for tryptophan. So that is what our Zwitter ion would look like. All right, for this one, we're looking at drawing amino acids that have a side chain with an acidic group. So our 2 acid amino acids are aspartic acid and glutamic acid. And when you're going to, if you have to memorize these for biochemistry, aspartic acid comes first in the alphabet for A, which will have that only has 1, 2 extra carbons off the alpha carbon. And then glutamic acid is later in the alphabet. This one has 1, 2, 3. So that's how I remember those ones. Those are the 2 amino acids that have carboxylic acid side chains. All right, so why don't you look at these and tell me which ones will participate in hydrogen bonding. All right, so let's look at these. Ones that will participate in hydrogen bonding can be acidic. They can be basic. So remember, things that can hydrogen bond are NHs, OHs, carbonyls, and those are going to be the side chains, not the main chain there. NH, OH, carbonyl, and we don't have any Fs here, so we don't have to worry about that. So alanine cannot, glycine cannot, isoleucine cannot. Let's see, none of the ones in the top row. Tryptophan can, because of this NH right there. Tyrosine can hydrogen bond. These two can. Arginine and histidine, lysine, and then these two right here. So those are the amino acids that can hydrogen bond. Questions there? All right. Draw the form of L-glutamic acid that predominates at each pH. So this table here tells us what is going to be protonated at what pH, or tells us what the pKa is. And when I was taking biochemistry in undergrad, my professor made me memorize all these pKa's, which was miserable. For me right now, it's not difficult just because I'm so used to these numbers. So this might be something you should be prepared for. But we're looking at glutamic acid, which is right here. So it tells us the alpha carboxylic acid has a pKa of 2. So this one is around 2. 2.2. The NH is around, we'll call that 10. And then this one is 4.25. So at a pH of 1.9, that is below all of the pHs on, or the pKa's on that amino acid. So that means that everything is going to be protonated. So for A, we'll have that. So our carboxylic acids are protonated. My NH2 should become an NH3+. So our overall charge on this particular structure here is positive. All right, so we did A. At 2.4, that one is slightly less acidic than the alpha amino acid. So the alpha amino acid there may be deprotonated. So for B, and that's on the alpha, not the side chain. So the side chain will be protonated. We'll have an NH3+. And then this one will be O-. So our overall charge at 2.4 is neutral. There's no charge here. At a pH of 5.8, that is less acidic, so there's less protons available. That one is over the side chain, so all of those things will be deprotonated. And our NH3 will still be there. Our overall charge here will be -1. All right, so why don't you try D and see what you get for that one. All right, so 10.4 is much less acidic than all of the pKa's. So hopefully you drew everything with no extra protons. So for D, we have O-, And then we have NH2, O minus. So our overall charge on this one is -2. Questions there? All right, so for each of the following amino acids, draw the form that is predominant at physiological pH of glutamic acid. I think we just did that. Okay, so the one for glutamic acid will look like the one at pH 5.8. So we'll have 2 O minuses. That should be NH3. Questions here? All right, here is, we're drawing a tripeptide here. And a peptide is an amide bond. So when you're doing these problems, I like to redraw them to make my life a little bit easier. And the way that I do that is I'm gonna put the NH2 over here. Have the alpha carbon with my side chain. So I'm just gonna put R1 for the side chain for now. And then I have the carboxylic acid. This one is going to be R1 for now. And then the lysine will be R2, R3. So if you can see, I put the alpha amino acid over on the left, the carboxylic acid on the right. I'm gonna do that with the next side chain as well. So I have H2N. This is R2. I have H2N. This is R3. And if you remember, the amide bond is carbon, or NH2 to a carbonyl. And we can make those, or we've seen them made using carboxylic acid plus NH3 or something similar. And that is happening via a condensation reaction where water is lost. So you can think about losing water here, and one of those H's off of the N, and then we lose one of those waters there. So now you can sandwich them together. So I have NH2, new bond to the next amino acid, which is N. There's a new bond to the next amino acid. Oops, there's an N there, alpha carbon. All right, so there's our tripeptide. And the only thing we have left to do now is to draw the zwitterion part of it. So at physiological pH, the NH2s will become NH3s. And then the carboxylates, if we have any of those, will be decarboxylated. So this will be NH3. And my side chain will be decarboxylated. And because amino acid sequence matters, the Aspartic acid comes first, then lysine, then phenylalanine. All right, any questions there? All right, that was the last of the amino acid questions. So anything like this you would see on the exam will be questions like, you know, which is this amino acid acidic, basic, polar, nonpolar, that type of thing. You may be asked to draw a dipeptide or a tripeptide, which is the one that we just did, or to draw an amino acid at different pHs. All right, so I will open the floor for questions. If you have questions about anything exam related, chapter 25 related, or otherwise, you can feel free to ask in the chat, or you can verbal ask.